Honors Chemistry. This is, we're beginning our third unit, which is on gas laws and how gases react and how they interact with each other. This is Lesson 16, Basic Gas Laws. So if the kinetic energy overwhelms the Coulombic attractions, then the molecules separate and exist as gas or vapor. So substances can exist in three states: solids, in which the atoms or molecules stick together very tightly and can't move. They can wiggle, but they can't move around. In liquids, they can move around, but they keep in touch with each other. They continue to touch other molecules next to them, but they can move around. That's why liquid water can slosh around. In gases, what happens is there's enough kinetic energy in the molecules, these are water molecules here, to actually allow them to separate. They have a weak attraction, they're polar molecules, so they're attracted to each other. They like to stick together, but it's not a very strong attraction. So if enough energy can be put into them, they'll break apart from each other and even break away from the Earth's gravity and start to float upward into the atmosphere. And so when that kinetic energy overwhelms that attractive force that they have between them, called Coulombic attractions, then the molecules separate and they exist as gas or vapor. The word gas has nothing to do with gasoline that people buy to put in their cars in gas stations. That's simply the name of a chemical formula, a chemical compound that's used to power cars. Gas in this sense means anything. It could be any kind of substance in which the molecules have broken away from each other. So the study of gas laws treats atoms, molecules, or ions in gas state as though they're little balls. We're not really interested for this particular lesson. We don't care about protons, neutrons, electrons. We don't get involved in that. We're not talking about chemical reactions at this point. We're just talking about how these little objects float around and how they interact with each other and what affects things such as how their speed, how much pressure they'll put on the container, and things like that. So since the gas can either be an atom, a molecule, or ion, we use the generic term particle. So when you hear particle, it just means it could be a helium atom of gas, it could be an H2 or an O2 or an H2O molecule, or it could even be an Na plus or a Cl minus ion. Rarely do we talk about ions becoming gases, but sometimes they do. Generally, it's molecules or atoms. So gas particles don't randomly change direction. They appear to be just randomly moving around and changing directions. So you have to imagine that these particles are changing direction because they're encountering other particles that you can't see, or they're hitting the sides of a container. This gives gas particles their apparent random motion. Heating and cooling can also cause particles to change direction. So if you think of something, a container with a really strong smell in it, like perfume, for example, and you open that up, especially on a warm day, maybe 10 or 15 minutes later, you'll be able to smell that all throughout the room. Or if you just spray air freshener in the air, eventually you'll be able to smell that throughout the room. And that's because the particles of that scented either perfume or air freshener will bounce off of other molecules, air molecules mostly, and move to different parts of the room. So gases can take part in chemical reactions. Here's a reaction that we've seen before. 2H2 plus O2 gives you 2H2O. You notice that the states all say G. They're all gases. Water can be produced from hydrogen gas and oxygen gas. And of course, water could be in liquid form as well, but we're assuming in this particular example that it's going to be in gas form. In this unit, we are only interested in how gas particles behave due to four factors. The first is the pressure of the atmosphere. The second is the temperature of the atmosphere. Third is the volume of the container. And fourth is the number of particles measured in moles. So how many of those groups of 6.022 times 10 to the 23rd do we have? So really we're talking about how do gases react in response to these four different variables. Pressure is the amount of force per unit area. That's a formula you learned in physics. The force is simply a push or a pull. So those particles are pushing on the sides of a container, and you take the number of pushes or the amount of the push in terms of force, and it's usually measured in a unit called newtons, and divide that by the area over which they are striking. then that will be the pressure. So the pressure of a gas can be thought of as the frequency with which gas particles hit the sides of the container. The units of measurement for gas law variables are: temperature is measured in Kelvin, volume in liters, moles is simply a number of moles, and pressure now has 5 different units of measurement. Why 5? It's just they evolved from different areas of study, and so you need to understand, though, to do these problems, how to convert from one measure to the other. So the 5 measures are atmospheres, the ones that we're going to use primarily in this class, pascals, kilopascals, torr, and millimeters of mercury. So 1 atmosphere is the normal air pressure at sea level. So the amount of air pressure you feel on your skin right now is 1 atmosphere. You may say you don't feel any pressure, but that's just because you're used to it. There's actually 14 pounds per square inch. So think of 1 square inch on your skin, 1 inch by 1 inch. There's 14 pounds of pressure on that and on every square inch of your skin. So it's amazing. There's a lot of air pressure on you, but we've developed to where we don't feel it. And so you may think you don't feel any pressure from the air, but you're definitely feeling pressure from the air. The following are conversions between the units for pressure. So 1 atmosphere, which again is the pressure that you're feeling right now being at sea level, equals 760 millimeters of mercury, equals 760 torr, equals 101,325 pascals, which equals 101.3 kilopascals. So all 5 of those are the same amount of pressure, just measured in different units. In the same way you made conversions between grams and moles, you can make conversions between any 2 of the measures above. Why there are 5 different units of pressure is something you don't need to understand, just know how to convert between them. So there they are. So we'll do a few example problems here. So how many kilopascals in 2.3 atmospheres? So what you're trying to find, where the question mark would go, is kilopascals. You're trying to find out how many. And what you're starting with is 2.3 atmospheres. So what you need to do is look up above at the red conversions there and just find the 2 that you're interested in, which is atmospheres and kilopascals. So there's 1 atmosphere equals 101.3 kilopascals. Now you have to do what you've done before in conversions. You have to decide which one goes on the top and which one goes on the bottom. Since we want atmospheres to go away, to disappear, cancel out, and kilopascals to end up in our final answer, we put the 101.3 kilopascals on the top and the 1 atmosphere on the bottom. Atmospheres cancels, and if you do the math on that, you get 233 kilopascals. Okay, this one. How many millimeters of mercury in 1.05 atmospheres? So go ahead, see if you can set that one up. And 1.05 atmospheres goes on the left, millimeters mercury goes on the right. So we need the conversion between those 2, which is 1 atmosphere equals 760 millimeters of mercury. Since we need atmospheres to cancel again, then atmospheres cancels with atmospheres. It has to go on the bottom of that ratio, and the 760 millimeters of mercury goes on the top. Now you just do the math. 1.05 times 760 gives you 798 millimeters of mercury. One more. How many torr is 98,600 pascals? So 98,600 goes on the left. Unknown number of torr goes on the right, and you need the conversion between torr and pascals. 760 torr equals 101,325 pascals. So this torr goes on top, pascals goes on the bottom, so it will cancel. So pascals cancels with pascals, and you do the math on that, and you get 739 torr. So temperature is the average kinetic energy of the molecules. So the molecules in gases, they move around, but they don't all move at exactly the same speed. Some are going to be a little faster, some are a little slower at a particular temperature. So the temperature is the average kinetic energy. It's the average amount of motion energy in those particles. So I said molecules here, but it could be an atom, it could be an ion, it's particles. This translates to meaning that higher temperature increases the speed of the molecules or particles. So here you go, you have a hydrogen molecule moving at a certain speed because it has a certain temperature. If you heat up that molecule over there on the right, then it moves faster. So increasing temperature increases the speed of the particles. Decreasing temperature will decrease the speed of the particles. So temperature is the average kinetic energy of the gas particles. Kinetic energy is given by the formula that you may have seen in physics. Ke, kinetic energy, equals 1/2 mass times velocity squared, where m is mass, v is velocity, which we can just think of in this class as speed. It's how fast it's going. By increasing the temperature, we increase the average kinetic energy of the particles. Since the mass of the particle remains constant, that H2 molecule is going to have a mass of 2.02 atomic mass units. That doesn't change. Then increasing the kinetic energy increases the velocity. If you look at that formula up above, Ke equals 1/2 mv squared. If Ke gets bigger and the m in that formula on the right cannot change, then the only other thing on that side of the formula that can change is the velocity. That has to get bigger as well. So increasing temperature increases the kinetic energy in the molecule, which increases its speed. So higher temperature, faster speed; lower temperature, slower speed. So let's say we have particles of two different masses in a container at the same temperature. This means they will have the same kinetic energy. So let's just make an assumption here. Assume the mass of particle A. We have particle A and particle B. The mass of particle A is 2 atomic mass units, and the mass of particle B is 8 atomic mass units. So particle B is 4 times more massive than particle A. And since they're at the same temperature, that means they're both going to have the same kinetic energy. So let's see how their speed of the two particles compares. Let's see how the speed of the particle that's 4 times more massive compares to the speed of the particle that's 4 times less massive, or 1/4 as massive. So there's the formula again for kinetic energy. So both particles have the same kinetic energy, 16. So we can compute the velocity for each particle. So for particle A, Ke is 16 equals 1/2, and then the mass of particle A is 2 times velocity of particle A squared. So we're doing a little algebra here to solve for the particle velocity A. I won't ask you to do any of these algebra problems here. And when you do that, you find that the velocity of particle A is 4. What the 4 represents, meters per second or whatever, it doesn't matter. We're trying to find the relative speed of the two, how much faster one is than the other, not really specifically how fast it's going. So we're just going to say for this example, the velocity of particle A is 4. Now we're going to do the same thing with particle B. Kinetic energy is still 16 because it's at the same temperature, equals 1/2. Now the mass of particle B is 8 times the velocity of particle B squared. You solve for particle B and you get a velocity of particle B of 2. So let's see what the relationship is between those two. The particle that is 1/4 as massive, that's particle A, moves twice as fast. Or another way to think of it is the particle that's 4 times as massive, that's particle B, moves half as fast as particle A. So you see there's kind of a mathematical relationship to that, and so we're going to see what that relationship is and how you could calculate that. So the 2 atomic mass unit particle moves 2 times faster than the 8 atomic mass unit particle. So the 2 atomic mass unit particle moves 2 times faster than the 8 atomic mass unit particle. This leads to the following relationship for 2 gas particles called Graham's law of effusion, and we're going to talk about effusion at a later time. So the speed of the lighter particle compared to the heavier particle is equal to, you take the mass of the heavier particle, divide it by the mass of the lighter particle, and then you take the square root of the quotient of the result of that division. So mass of heavier over mass of lighter. So in our example, how many times faster is particle A moving? Just common sense tells us that the lighter particle is going to move faster. So you take the heavier particle in our example in the previous slide, which was 8, divided by the mass of the lighter particle, which is 2. 8 divided by 2 is 4, and the square root of 4 is 2. And that's what we got on the previous slide, that the lighter particle, particle A, was moving twice as fast as particle B. Temperature. So in this class, when we talk about temperature, we're talking about two temperature scales. The centigrade scale, sometimes known as the Celsius. A lot of students know it as the Celsius scale. It's the same thing. And then the Kelvin scale. The scale that we use here on the United States, if you watch TV news and hear the weather person talk about the temperatures, is the Fahrenheit scale. So if they say it's 70 degrees in San Diego, what they mean is 70 degrees Fahrenheit. We never use the Fahrenheit scale in chemistry. We only use the centigrade and the Kelvin scale. So what's the difference between the two? Well, let's look at the centigrade scale first. A centigrade scale is based around the properties of water. In fact, the whole metric system is based around properties of water. So what they decided when they made that scale was the freezing point of water. There's 3 states of water: solid, which we call ice; liquid, which we just call liquid water; and vapor, which we call steam or water vapor. So the changing point between those states, between solid to liquid, is called the freezing point of water. That's where ice becomes liquid water or water freezes to liquid ice. They decided to call that 0. And then at the point where liquid water boils, like you put a pan on a stove and the water starts to boil off, that's the boiling point of water. They decided to call that 100. And then they just divided that difference into 100 different little pieces. And so the word centigrade means centa meaning 100, grade meaning gradations or parts. So centigrade means 100 parts. So there's 100 parts between the freezing point and the boiling point of water. All right, now that's a very practical scale, and it's used in most parts of the world. Most temperatures are recorded in centigrade. But scientists said we need a different scale. We need a scale where 0 really means 0. It is the absolute lowest temperature that you could have in the universe. And so they came up with the Kelvin scale. So 0 on the Kelvin scale means you are at the lowest point. There's nothing below 0 Kelvin in the universe. What it really means is that an atom has lost all of its energy. All of the energy has been taken out of the atom, and its electrons, which are flying around the atom, just collapse into the nucleus. And that's what 0 degrees Kelvin represents. There's no negative numbers on the Kelvin scale. But when they developed the Kelvin scale, they decided that a degree on the centigrade scale would still be a degree on the Kelvin scale. So look at the centigrade. There's 100 degrees, 0 to 100, between the freezing point and the boiling point of water. Now go over to the Kelvin scale, and you'll notice there's also 100 degrees between the freezing point and boiling point of water, from 273 to 373. What that means is a degree on both scales is the same amount of kinetic energy change. If you take 1 degree on either of those scales, it's the same amount of kinetic energy change. However, the only difference between them is what they decided to call 0. The centigrade scale calls the freezing point of water 0, whereas the Kelvin scale calls the absolute lowest possible temperature in the universe 0. So absolute 0 is the lowest possible temperature in the universe. It is 0 K on the Kelvin scale and negative 273 degrees centigrade on the centigrade scale. A degree on both scales is the same change in kinetic energy. The only difference is what each scale defines as 0. So to convert from Kelvin to centigrade, just use a very simple formula. Centigrade plus 273 will equal the temperature Kelvin. To convert from centigrade to Kelvin, you just use the reverse of the formula. You take the Kelvin, subtract 273, and that will give you the degree in centigrade. Just remember, a Kelvin temperature numerically is always going to be bigger than a centigrade temperature. All right, so here are some examples of conversions. They're pretty straightforward. If you have convert 25 degrees centigrade to Kelvin, so 25 plus 273 is 298. That, by the way, is a number that's used a lot in chemistry problems because it's normal room temperature. 25 degrees centigrade is roughly normal room temperature. So you'll see that number a lot. Convert negative 35 centigrade to Kelvin. So negative 35 plus 273 gives you positive 238 Kelvin. Convert 313 Kelvin to centigrade. So now you're going back in the other direction. 313 minus 273 equals 40 degrees centigrade. And convert 260 Kelvin to centigrade. So 260 minus 273 is negative 13 degrees centigrade. So again, just remember Kelvin temperatures are always numerically larger, higher than centigrade temperatures, the equivalent centigrade temperature. So volume is the amount of space that an object occupies in 3 dimensions. In some cases, the volume can change, such as with a balloon. In other cases, the volume can be fixed, such as a glass or metal container. Oftentimes, when you read a chemistry problem, you want to be looking for words such as that it is a balloon, or the volume, or they'll suggest that the volume can change. If you're reading a chemistry problem and it says that a reaction takes place in a rigid container, that means that it's something like glass or metal that cannot expand. So that would mean the volume in that problem is going to stay fixed. Volume is measured in liters. You all know what a liter is. You've bought liter bottles of water or 2-liter bottles of soda. Often in chemistry, volumes are measured in milliliters, and there are 1,000 milliliters equals 1 liter. Again, go back to your units conversions way back about lesson, about lesson 2 or 3 or 4, where it has all of these conversions between milli and micro and so forth. But this one is really the only one you're going to come across for volume in chemistry. It's milliliters to liters. So example, convert 467 milliliters to liters. So 467 milliliters times 1 liter for every 1,000 milliliters. You need the milliliters to cancel out. Whoops, thought that was going to cancel for me. So you need the milliliters there to cancel out top and bottom, and that's going to equal 0.467 liters. So here's an important volume relationship that you'll run across occasionally, and that is centimeters and liters, or really centimeters and milliliters. That 1 cubic centimeter is a little less than a half an inch. So if you take that little less than a half an inch wide by high by deep, make a little box out of it, a little cube out of that, that's the equivalent of 1 milliliter. So if you see centimeters cubed, it's the same as a milliliter. Okay, there's one major formula that relates all 4 variables of gases, and that's called the ideal gas law. And it's PV equals nRT. So PV, T, and N have previously been defined. That's pressure, volume, temperature, and number of moles. R is called the ideal gas constant, and it's equal to 0.0821 liter atmospheres over moles Kelvin. The purpose of this constant is it cancels the units of measurement so that only the units of the final answer appear. So I'll show you some examples of that. The ideal gas law is the central formula for the study of gases. An ideal gas is a gas in which the gas particles don't interfere with each other. If you could think about a single atom or molecule or particle of gas in outer space where there's no other gas particles around, so it's not going to bump into anything, nothing's going to interfere with it, that would be an ideal gas. That's a simple way to think of an ideal gas. So the ideal gas law is PV equals nRT, where P is pressure, and that's measured in atmospheres. V is volume in liters, N is number of moles, and T is temperature in Kelvin. R, the ideal gas constant, equals 0.0821 liter atmospheres over moles Kelvin. So think of the gas constant as several conversion factors wrapped into one number. R causes all units to cancel except the one needed in the final answer. So let's see an example of that. So PV equals nRT. Think of the gas constant as 6 conversion factors wrapped into one number. Why 6? Well, it's going to convert between pressure and volume, between pressure and number of moles, and between pressure and temperature, so that's 3, Then between volume and number of moles, and volume and temperature, that's 2 more, that's up to 5. And then between number of moles and temperature, that's a 6th. So it's 6 conversion factors all wrapped into one number. So example, you solve for temperature. If you do that by dividing both sides by N and R on the formula above, and you get PV T, temperature, equals PV over NR. So that the gas constant in that position where it's located down there on the bottom will cause all units of measure to cancel except Kelvin, and that's the unit for temperature. Okay, and we'll see an example of that with numbers coming up here in a little bit. Okay, what happens to pressure when volume is increased? So the best way to understand these relationships is just every time you're asked a question like that, how is one of the variables going to affect the other? A change in one of the variables going to affect the change in the other? Write the formula out and just draw arrows indicating which way it has to move. In other words, think of it mathematically, not just in terms of physically what's happening, but mathematically what's happening. So what's going to happen here is, look at this equation. If we want to know how a change in pressure is affected by a change in volume, we look at those two variables. Those are the ones in red. That means everything else is going to remain constant. The number of moles, so you're not going to add or take away any of the gas, and the temperature. That means the speed is going to stay the same of the gas particles. Okay? So if N, R, and T remain constant, then as V increases, P decreases. So think about that mathematically, just looking at that equation. If you want N, R, and T to equal a certain number, if they equal a certain number before the change, and then all of a sudden you increase the volume, what are you going to have to do to the pressure so that N, R, and T still equal the same number? They don't change value. And the answer is you'd have to reduce it. So let me just give you a quick example. If you doubled the volume, you would have to cut the pressure in half in order for P times V to still equal the same value of N, R, and T. So just think of it in those math terms. Okay, so the relationship between pressure and volume is called Boyle's law. So let's look at an example. Here, the temperature is not going to change. So that means this hydrogen molecule is going to have a certain speed moving around its container. Now we think of pressure as how many times a particle hits the sides of the container. We talked about that a little earlier. Okay, so now what we're going to do is we're going to take that same particle and we're going to put it in a larger container over there on the right. And so now the two particles are moving the same speed. They have the same temperature, that hasn't changed, and we haven't increased the number of particles. There's one particle, or you can think of it as 1 mole if you want, in each of those containers. There's 1 particle in each container. So if you increase the volume, what does that mean in terms of pressure? Well, if pressure is the number of times that the particle hits the side of the container, then if you give it a bigger container, it's going to have to travel a farther distance to hit the sides. That means it's going to hit the sides fewer times. Therefore, that's less pressure. So let's say that again. They're both moving the same speed, but the one on the right is in a larger container. You've increased the volume, so it has to travel a longer distance to get to each of the sides. That means it's going to hit the sides fewer times than the particle on the left, which is in a much smaller container. So the pressure of the particle on the right, the larger container, as you increase the volume, the pressure is going to decrease because the number of times it hits the container is going to decrease. And that's called Boyle's law. Okay, what happens to pressure when temperature is increased? So there you see the formula. So what's going to change is the letters in red, pressure and temperature. Everything else stays the same. So the volume's going to stay the same. The two containers down below are the same size. That's going to stay the same. And you're not going to add or subtract any gas from the container. So the number of moles or number of particles is going to stay the same. So just look at it mathematically. What happens to pressure when temperature is increased? So if you increase temperature, which is on the right side of the equal sign, mathematically you're going to have to increase pressure to keep all the other variables the same, to keep the equation in balance. So again, if you were to double the temperature, you would have to double the pressure. Multiply the temperature by 2, you'd have to multiply the pressure by 2, assuming that the others can't change. So increasing the temperature is going to increase the pressure. So let's see why that is. If N, R, and V remain constant, then as temperature increases, P increases because the particle hits the sides more times. So there we have the particle. It's at a certain temperature, so it's moving at a certain speed, and therefore it's hitting the sides of the container a certain number of times. If we then heat it up, say like put a flame underneath the gas, now it's going to move faster. Increasing temperature causes the particle to move faster. And what that means also is that it's going to hit the sides of the container more often than the one on the left. And so that means the pressure is going to be increased. Pressure is how often that particle hits the sides of the container. So the relationship between pressure and temperature is called Gay-Lussac's law. What happens to volume when temperature is increased? This one's a little trickier to understand, but it's not that hard. So assume everything else remains, all other variables remain constant. So again, look at the equation. Learn how to just kind of understand mathematically what's going to happen. If you increase T over there on the right of that equation, you're going to have to increase V over on the left. So again, if you were to double T, multiply it times 2, you'd have to double V, the volume, multiply it times 2 in order to keep the equation in balance. So if two variables are on opposite sides of the equal sign, an increase in one is going to lead to an increase in the other. If they're on the same side of the equal sign, such as pressure and volume in Boyle's law, then as one of them goes up, the other one's going to have to go down. So if N, R, and P remain constant, then as T increases, V increases. For the particle to hit the sides the same number of times, constant pressure, because that's what constant pressure means, it's they're hitting the sides the same number of times, while moving faster at a higher T, the volume must be bigger. Okay, so let's look at this. So there you have a particle at a certain temperature, and it's moving around. I timed this so it's moving around one time every 2 seconds. So 1 second, 2 seconds. So it hits the sides, if you count it, it hits the sides 4 times every 2 seconds. So that the number of times it hits the side is going to tell you what the pressure is going to be. Well, if the pressure is going to stay the same on the balloon on the right, it has to hit the side the same number of times, which is 4 times every 2 seconds. So we're going to go ahead and make that one go around. Okay, but you've increased the temperature, so the particle on the right is moving faster because it's under higher temperature. If it's moving faster, but you want it to hit the sides the same number of times, that's keeping the pressure equal to the one on the left, then the only way to do that is expand the balloon, is make it have to travel a farther distance. So both particles are hitting the sides the same number of times, but since the particle on the right has to travel a farther distance, it's moving faster, it's going to have to travel a farther distance in order for that to happen. Okay, so the only way to keep the pressure the same if you increase the speed of one of them is to make the balloon bigger and make that particle have to travel a farther distance. So they're both hitting 4 times every 2 seconds. All right, so this is called Charles' law. What happens to pressure when the number of moles is increased? So PV equals nRT. So just mathematically, P and N are on opposite sides of the P and N are on opposite sides of the equal sign. Therefore, if one of them goes up, the other one has to go up. So if you double the number of moles N, you're going to double the pressure to keep the equation in balance. So if T, R, and V remain constant, then as the number of moles increases, P increases because there are more particles hitting the sides. The relationship between pressure and number of moles or number of particles is called Avogadro's law. So if at first, let's just say we have one particle in there, and it's hitting the side 4 times every roughly 5 seconds, we'll say it is. Okay. Then if you double the number of particles at the same temperature, that means they'll be going the same speed, then you'll have particles hitting the sides twice as many times simply because you have twice as many particles. That means your pressure will also double. So that's what Avogadro's law is. It relates pressure to the number of particles or number of moles that you have. Okay, so that takes care of our basic gas laws, lesson. And now in the next lesson, we're going to move on to stoichiometry of gases and how we use gases in chemical equations.